Okay, number 46. This problem has it all. This problem, you're going to be using both of the major ideas in chapter 19. Now, what are the two major ideas in chapter 19? The two major ideas are, number one, what do magnetic fields do? They exert force on moving charged particles. Look at, in this problem, where do we find our moving charged particles? We find our moving charged particles as current. Remember, current moving through a wire is nothing other than moving charged particles, okay? And we always define current as being positive charge motion. Okay, that was major idea number one. What's major idea number two? Major idea number two, where do magnetic fields come from? They come from moving charged particles, which again is current in a wire. So for starters, in this problem, so this is wire number one, and then over here we have wire number two with a current in it. And then, kids always look at this, they're like, well, where's the battery? Because typically you have a battery if there's going to be current. Don't worry about it. There's current in this wire, and we're given what these currents are. I1 is 5 amps, and then I2 is 10 amps. Okay, in this problem, wire number one, this guy, is the source of the magnetic field. Wire number one creates the magnetic field. It's how the problem is worded. Okay, now what's wire number two doing? Wire number two is sitting in the magnetic field that wire number one created, and it's going to get a force. Remember, moving charged particles in a magnetic field will get a force. So wire number one creates the magnetic field. Wire number two is sitting in that magnetic field and is going to get a force. Okay? So a few things. Let's focus on wire number one here for a second. So I want to erase, let's get rid of wire number two. Let's just temporarily remove wire number two. Now what's the magnetic field around wire number one doing? Well, to do this, to figure out what the magnetic field's doing, you have to use right-hand rule number two. You stick your thumb in the direction of the current, and then the way that your four fingers curl is the direction of the magnetic field. So for wire number one, we have a magnetic field going into the page or into the screen on this side and then out on this side. Now, how do you find the strength of a magnetic field around a wire with a current in it? Well, you're going to use this equation right here. This is the equation for finding magnetic field at a distance from a wire. So for example, if you wanted to find the magnetic field like over here, like at this point right here. So R is the distance from the wire, I1 is the current, mu naught is a constant, okay? So notice the farther you are from the wire, the weaker the magnetic field becomes. Does that make sense? So the magnetic field is traveling in a circular path around wire number one. It's going into the page on this side, it's going out of the page on this side. Okay, now let's revert this. Okay, so now let's look at what's happening to wire number two. So we've already established that over here, the magnetic field's going in, right? Because in this problem, wire number one creates the magnetic field. So the magnetic field's going in. Now, let's figure out the direction of the force on wire number two. So focusing on this top segment, which way is the force on this top segment that I'm circling? Well, you got to do right-hand rule number one. So magnetic field goes in, right? Your thumb points to the right because that's the way the current's going. The palm of your hand faces up. So the force here is up. Now let's do the same thing for down here. Right-hand rule number one. So your four fingers are going in. Your thumb now points to the left. Which way is the palm of my hand? Down. So look, what will be happening to this force and this force. Those forces will be canceling no matter where you look. I mean, so what if we would have looked like over here a little bit more to the left? So we'd have an up force, but then go to the identical spot down here, and we'll have a down force, right? At every point, you know, if you look there or there or there, at every point you're going to get an identical up force and an identical down force. So will the net force be vertical? Is it going to be in this direction? Oh, and by the way, what are we looking for in this problem? The thing we're looking for is the net force on wire number 2. Okay? So it's not going to be in the vertical direction because the forces in the vertical cancel. Okay, so now let's look. So magnetic field's going in over here, in, like this. So now let's look at this segment of the wire and this segment of the wire. So which way is the force on this segment of the wire over here going to be? So do right-hand rule number 1. The force will be that way, right? Magnetic field's going in, current's going down, the palm of our hand faces to the right. Okay, come over here to this segment of the wire. The force is going to be to the left, right? The force is going to be this way. Okay, now let's call this force left. We'll call this force right. Which force is going to be bigger? Now, this is like one of the key insights of the problem. Which force is going to be bigger? Force left or force right? Force left. Why will force left be bigger? For one reason. The magnetic field in this region right here, the magnetic field is stronger here than it is over here. Why is the magnetic field stronger in this region? Because it's closer to the source of the magnetic field. Okay? So here's what we got to do. So let's actually solve this now. So we've talked about the theory, and so let's actually do it. So what we got to do is so this is wire number 1, this is wire number 2, current 1 is 5 amps, current 2 is 10 amps. What we need to do is find out the magnetic field strength here and here. Okay? So the magnetic field strength there, you're going to go B equals mu naught I over 2 pi r. When you do that, you find out, so you plug all the numbers in, the magnetic field strength comes out as 10 to the negative 5th Tesla in this region right there. Okay, over here, the magnetic field strength comes out as 4 times 10 to the negative 6 Tesla, again using the same equation. Now, our forces. The force on this segment here, right? The equation we use is F equals BIL, which is really just QVB, but it's for when you have charges moving in a wire. Yo.
Why is it 4 times 10 to the negative 6 Tesla? Like, I got like 4 times 10 to the negative 6.
Maybe I made a mistake. So look, the way I got this one, let me show you how I did it. So 4 times 10 to the negative 6, the way I did it, so we go like this. We go mu naught I over 2 pi r. So mu naught is 1.26 times 10 to the negative 6 Tesla meter over amp. The current is 5 amps divided by 2 pi times 0.25. Let me punch this in. Here, let me pause the video. Okay, so we just confirmed. So this comes out as 4 times 10 to the negative 6 Tesla. Now, the next thing we do, we got to calculate force right, and we got to calculate force left. Okay, so to find force right, you're going to go BIL sine theta. What's the theta here? It's the angle between the current and the magnetic field. So it's 90, and sine of 90 is 1. So force right, B, so force right, it's going to be this. 4 times 10 to the negative 6 Tesla. The current is 10 amps. And then the L is this distance here, which is 0.45. So force right comes out as 1.8 times 10 to the negative 5. Okay, and then force left is going to be the, so let me write this down. So force right is 1.8 times 10 to the negative 5. Okay, now, how do we get force left? Just change the R to L. Force left is going to be the exact same equation, only what's different? The magnetic field over here, what was the magnetic field over there? 10 to the negative 5th. Right? And then everything's the same. So force left comes out as 4.5. 4.5 times 10 to the negative 5. So we got that right here. This is equal to 4.5 times 10 to the negative 5. Now look, which force is going to win? Force right or force left? Force left. So then you subtract those. It's kind of like a tug of war. You got force left, 4.5 times 10 to the negative 5. And then we also have force right, which is smaller. Oops, I should make that smaller. Force right, 1.8 times 10 to the negative 5. So then the answer is going to be the difference between those, which is 2.7 times 10 to the negative 5 to the left.